Okay, now we will continue with electrochemistry. So in that we will discuss electrode potential. Now in order to define this, what is an electrode potential? Let us take a metal zinc is in contact with a zinc sulfate solution, or a copper metal is in contact with the copper sulfate solution. This is aqueous solution. Now zinc is in contact with the zinc 2 plus ion, its own metal ion. Copper is contacted with copper 2 plus ion, its own metal ion. Now the zinc is actually undergoes oxidation. Now zinc will undergo oxidation, and copper will undergo reduction. Copper will undergo reduction. Now we can define the electrode potential. The electrode potential is nothing but the natural tendency of a metal to undergo oxidations. It is a natural tendency of a metal to undergo oxidations or a reduction. Oxidation or a reduction reactions when contact with an aqueous solution of its own ion. When contact with an aqueous solution of its own metal ion. Now this natural tendency we call it as an electrode potential. The natural tendency of a metal to undergo oxidations or reductions when a metal is in contact with its own metal ion in an aqueous solution. So this is we expressed as a electrode potential. Now the oxidations and reduction reactions that occurs may be represented as, so here zinc will undergo oxidation. It's a natural tendency of a zinc to undergo oxidations, and copper will undergo reduction. It's natural tendency when in contact with the copper sulfate solutions, the copper will undergo reductions. Now the oxidations and reduction reactions that occurs may be represented as, so we can take zinc, it will become zinc 2 plus and 2 electron, and here copper 2 plus 2 electron, so it will undergo copper 0. So this is, we call it as oxidation, that is the losing of electron, oxidation, and this is, we call it as a reduction. Now during the oxidations, what will happen is that the solid metal zinc, we have a zinc metal, now it will undergo oxidations. Oxidation, that means it will convert into zinc 2 plus. That indicates that zinc metal undergoes dissolutions. It undergoes dissolution. So because it has to give the Zn2 plus ions into the dissolutions, leaving the electrons there. So zinc metal gives Zn2 plus ion, leaving the electrons there. So it has a zinc metal. So zinc metal, okay, now it loses zinc 2 plus into the solutions, leaving the electrons here into the metal. And once the electron is leaving onto the metal, so the electrons actually naturally accumulate onto the solid metal, thereby making the metals acquires negative charge. So zinc metal acquires negative charge. Zinc metal acquires negative charge in comparison with the electrolyte, in comparison to the solutions. So in a similar fashions, in case of reduction reactions, now the copper metal acquires positive charge in comparison with the solutions. So once it acquires a positive charge, what will happen is that the copper 2 plus ion will undergo reduction, so it will deposited onto the copper metal. So the copper plus 2 will actually undergo reductions and deposited onto the copper metal. So one is actually dissolutions of the metal, one is depositions of the metal. So oxidations will actually accompanies with the dissolution of the metal, and the reduction will actually accompanies with the depositions of the metal when it is contacted with its own metal ion. And here the electron is actually furnished by zinc metal and utilized by the copper metal. So the electron here is actually furnished by zinc metal. Zinc actually donates electron, gives electron, and utilized by the copper metal. Now the rate at which the oxidations and the reduction reactions taking place will actually depends upon the rate at which the oxidation and reduction taking place will actually depends upon the nature of the metal. Nature of the metal. Next is actually temperature of the system. Temperature. And the third point is the concentration of the metal ions in the solution. So how much concentrations is actually there in the aqueous solution. Concentration of the metal ions in solution. In the oxidations and the reduction reactions, the metals, so the solid metals, one actually acquires the solid metals acquires positive or a negative charge. So once it acquires, the metal acquires positive or a negative charge, what it will happen, it will actually attract the oppositely charged ion. It actually attracts the oppositely charged ions from the solutions and actually forms a layer. And that layer we call it as Helmholtz electrical double layer. Now this actually represented like this. Now the zinc metal, it actually carries a negative charge, acquires a negative charge. The copper actually acquires the positive charge in comparison with the solution, so it actually attracts the positive. Now this layer, so this is metal. Now it attracts the negative charge. Now here it is positive. It will be positive here. Now this layer we call it as a Helmholtz electrical double layer. So it is double layer. Now this layer we call it as Helmholtz electrical double layer. And this electrical double layer is actually established at the interface between metal and the solution. So in between the metal and the solutions, there actually forms an electrical double layer, because metal carries one charge corresponding to the solutions. Solutions will have the metal ion, so the metal acquires one charge and the oppositely charged will be attracted by the ion. So this actually forms a double layer, and that double layer we call it as Helmholtz electrical double layer. Now the metal is in contact with the metal ion is called as a metal ion electrode. The metal is in contact with the metal ion, we call it as a metal ion electrode. And the salt solutions, that is the metal ion solutions, is called as electrolyte. So this is, we call it as a electrolyte. And this is electrode, the metal, we call it as electrode. Now the electrode electrolyte system, this system we call it as the electrode electrolyte system is called as a single electrode. This we call it as a single electrode or a off cell, we call it as off cell. So in a system we have two such cell, two single electrode which are electrically connected with one another, electrically connected from one another, then we call it as electrochemical cell. Then we call it as electrochemical cell. Now we will deal with the electrochemical cell in detail. Electrochemical cell. So electrochemical cell is a device in which the chemical energy is converted into electrical energy. Chemical energy is converted into electrical energy. Or in the reverse direction, so we can convert the electrical energy into chemical energy just by passing slightly above the output electric current. So this chemical cell, so this chemical energy gives up some electric current. This gives some output electric current, maybe plus 0.2 volts, say for example. Now just by passing a reverse, by just slightly by passing above output electric current 0.21 volts, if you pass into the chemical cell externally, now the electrical energy will be converted to chemical. The reactions will go in the reverse order. That is how the electrical energy converts into a chemical energy, by passing just slightly above the output electric current. So an electrochemical cell, which actually utilizes the oxidations and reduction reactions occurring within the cell to generate electricity. So it's generally known as voltaic cell or a galvanic cell. Generally known as voltaic cell or galvanic cell. So this cell actually generate electricity that's based on the reaction that occurs within the electrochemical cell. The reactions is nothing but oxidations and reductions reactions. So a galvanic cell consists of two off cells, that is single electrodes, two off cells, so which are connected electrically. So it has to be connected externally. The electrodes, so it contains off cell, each cell contains electrodes, each cell connected with electrode and electrolyte, and these electrodes are connected externally by a piece of metal wire. So an electric current actually flows through the external circuit. So an electric current will actually flows through the external circuit. So why? Because here we have a zinc connected with zinc sulfate. We have a copper dipped in copper sulfate solution. So this actually loses electron, 2 electron. This actually accepts 2 electron. So this actually accepts. This actually gives up 2 electron. Now this is one off cell. This is another off cell. Now it is actually different container. Now this has to be. So when this gives off electrons, now what will happen? So if you connected an external circuit, just by a circuit, so the electron actually flows outside the circuit. It actually flows through the externally, it actually flows through the circuit. This is actually a Daniell cell. So now this is actually an example of galvanic cell is a Daniell cell. Daniell cell. So an example of galvanic cell is nothing but a Daniell cell, which actually contains a zinc rod immersed in a zinc sulfide solutions, electrolyte, and a copper rod is actually dipping in copper sulfide solutions. So they are kept separately in two containers. The two the electrolyte solution is all electrically connected to a salt bridge. Now this is actually connected through a salt bridge. So we can so which does not allow any chemical interactions between the two electrolytes. The two electrodes are connected externally through a galvanometer. Now you can see this Daniell cell. Now this is, so we have a two container. In one container we have a zinc rod is actually dipped in zinc sulfide solution. Okay, now in another is actually copper rod. We have a copper rod, it's dipped in copper sulfide solution. Now it's connected externally through a galvanometer. So galvanometer uses to measure, galvanometer or voltmeter is to measure the current passing through the circuit, external circuit. So this is copper sulfate, another electrolyte. Now we have a salt bridge. So this is a salt bridge. A salt bridge will have an electrolyte of KCl or ammonium nitrate. Now KCl and ammonium nitrate will have equal transport number. T plus and T minus are almost same. Now why we are using salt bridge? So in order to overcome any chemical interactions between the two electrolytes, and also in order to overcome the liquid junction potential, we will come across what is the liquid junction potential. Now the Daniell cell can be represented as, so this Daniell cell, this is galvanometer. Daniell cell can be represented as zinc dipped in zinc sulfate, the separation, copper sulfate, copper. So zinc is actually undergoes oxidations, and this is reduction. Now this is oxidations always will be treated as anode. So anode oxidations will undergo, and cathode, so reductions. So anode is a negative electrode, and this is a positive electrode. So that is why it carries negative charge. This carries a positive charge, and this is oxidations, and this is reduction. So while writing the notations of an electrochemical cell, first oxidation cell we have to write, and the reduction cell after that we have to write. Now the double stroke here, why we are using this double stroke is actually indicates the cell is actually free from the liquid junction potential. So the liquid junction potential, that potential arises in between the two electrodes when it is physically contacted between these two electrolytes. So if zinc sulfide is in contact with the copper sulfate, so naturally a liquid junction potential arises in between the two electrolytes. So that's what we call it as a liquid junction potential. Now we can avoid this liquid junction potential by separating these two electrolytes and connecting through salt bridge. Now this liquid junction potential actually arises between the two different electrolytes is due to the difference in the current carrying capacity. It's actually difference in the current carrying capacity. So one may carry more current, one may carry less current of the constituent ion of the electrolyte. So here we have zinc 2 plus and sulfate. So here zinc and sulfate, so it has uh, different transport number. If it is a different transport number, now the contributions from the each individual ion is different. Now this salt bridge actually consists of the salt bridge. The salt bridge consists of a concentrated solution of inert electrolyte, 1:1 inert electrolyte. It should be 1 plus ion, 1 cation and 1 anion. So KCl or ammonium nitrate. So 1 cation, 1 anion, 1 cation, 1 anion. That is 1:1 inert electrolyte. So the transport number of the constituent ion is almost same. So here the saturated solution of KCl or ammonium nitrate in agar gel is placed. Agar gel is placed in a glass tube. With the two ends of the tube is actually plugged with filter paper and a cotton. So this will be used as a salt bridge. Now the oxidations and reduction reactions at two electrodes can be represented as at anode, as I told, at anode. So oxidations will be taking place, that is zinc will undergo oxidation to form zinc 2 plus 2 electron, and at cathode copper 2 plus in the solutions will undergoes reduction and copper will be deposited on the copper metal. Now the overall reactions will be zinc plus copper sulfate, zinc sulfate plus copper. Now in the very important thing in the reactions that we remember is actually, so here what will happen is that the zinc, so this metal actually undergoes dissolution, so there will be a release of the zinc 2 plus ion. So there is an increase in the zinc 2 plus ion in the electrolyte, in the vicinity of the electrolyte. And if you come here, the copper 2 plus is actually undergoes reduction and deposited on the copper metal, so therefore diminishing the concentration of the copper 2 plus. So copper 2 plus in the vicinity of the electrode decreasing. On the other hand, zinc 2 plus in the vicinity of the electrode increases. Now there is a variations of the electrolyte concentrations. Now in order to avoid these variations, what will happen, the zinc 2 plus through the salt bridge it actually migrates. The zinc 2 plus it actually migrates to here. In order to, so if copper 2 plus diminishes, sulfate concentration will be increases. So in order to counterbalance the excess sulfate in the other container, the zinc 2 plus actually migrates through the salt bridge and accumulates the sulfate. Now there is no excess zinc 2 plus ion will be present here. So this is one of the advantage of the using salt bridge externally. Now here the electron is actually flows, the electron is this accumulated, the electron is actually flow from anode to cathode. So the anode electron is actually flow from anode to cathode. So electron is actually flowing from anode to cathode. So one electrode to another electrode. Now when a cell is actually connected with a galvanometer, the cell is actually connected with the galvanometer and the circuit is actually closed. So the galvanometer, as the reactions happens, the galvanometer shows a deflections indicating that the current is flowing through the circuit. So when the galvanometer shows any deflections, that actually indicates that the current is actually flowing through the external circuit. The flow of current from one electrode to another electrode is actually due to the potential difference between the two electrodes. So the current is actually flowing from one electrode to another electrode. It's nothing but there is a potential difference between the two electrodes. Now the potential difference which causes a current to flow from electrode of higher potential to an electrode of lower potential. So it's called as a EMF. Is that the electron is actually the current is actually flow. The current is flowing from one electrode to another electrode, so the current is actually flowing. It's due to the potential difference difference between the two electrodes. So the current is actually flowing from higher potential to a lower potential. So here the electrons, what the we need to make clarity of this. We have an anode and we have a cathode. So the electron is actually flow from anode to cathode, but the current I is actually flow from cathode to anodes, from higher potential to a lower potential. So the cathode's copper is actually plus 0.34 volts, zinc is actually minus 0.7 volts. So the current actually flows from copper to zinc, but the electron is actually flows in a reverse direction. So that is why it is actually designated by the symbol I. I means imaginary. So when the electron flows in the opposite direction, the current flows. Now the potential difference between the two electrode is, we call it as EMF. Now the current is actually flows from one electrode to another electrode, which is due to the potential difference between two electrodes. Now the current is actually flowing from higher potential to the lower potential, and that we call it as EMF. EMF means electromotive force. And this is actually responsible for the flow of current from one electrode to the another electrode. Now this EMF is actually measured in volts or millivolts. The voltage of the cell can be measured by a voltmeter. So this can be measured through a voltmeter. So which is connected across the two electrode. So the measured voltage will actually depends upon the current drawn by the voltmeter. The measured voltage will actually depends upon the how much current we actually drawn by the voltmeter, and the sum of the resistance of the external circuit. And the EMF will actually depends upon the resistance of the circuit, and the current drawn by voltmeter current, and internal resistance of the cell, external resistance as well as internal resistance of the cell. Now the electromotive force of the cell is actually maximum. It reaches to a maximum voltage. The EMF of the cell is nothing but it is the maximum voltage of the cell that can be measured when zero current is actually drawn during the measurement. Now such a measurement can be done by using a potentiometer. A potentiometer can be used to measure the voltage of a cell, that is EMF of the cell, when there is no current flows outside the circuit or externally. So when there is no current, zero current is flows, and zero current is flows through externally.